Welcome back. This is tutorial 5AZ transform. We are given a transfer function. We are told that it is for a causal system and it is represented by this HZ. We are asked to write a MATLAB code. Well, we can write Python code if you wish to generate the output of yn for this transfer function given xn equals to unit step, given xn equals to cosine, as well as the linear combination of this. The idea of this question is basically to show you how you can write a difference equation implemented in MATLAB to generate the output for different inputs. And because the system is linear and time invariant, then actually the output generated by here, for example, let's call this y1 of n, and let's say this is y2 of n. This guy is actually y1 of n plus y2 of n, the output for this input. That's the idea. Finally, in the last question, we are asked to plot the surface of HC from -2 to 2 and -2 to 2 along the imaginary. Let us begin. First, let's write down the difference equation. When you want to generate, this is the transfer function. When you want to generate the difference equation, the trick is that you have to convert from positive power to negative power. So all you do is times 1 over z, such that you will convert these positive powers to negative powers. Since 1 over z divided by 1 over z is 1, nothing has changed. But now hz is represented by negative powers of z, and you know that when we use negative powers of z, the inverse z transform actually introduces a time delay. The other thing we know is that hz is simply y over z divided by x over z. So what we do is that we move it to the right hand side for x of z, we move this to the left hand side for y of z, and then we get this equation over here. Now it's simply a matter of performing inverse z transform, and the only trick we are applying is that z minus 1 of y of z is simply yn minus 1, and we are moving from the left hand side to the right hand side. That is why the negative becomes the positive. So yz, so I write here yz times 0.9 z minus 1, this is simply 0.9, the coefficient, y of n minus 1. This n minus 1 is, remember, due to this z minus 1. Because the whole thing is now on the minus, when we move to the left hand side, it becomes positive. This is trivial. 1 times xz becomes xn, of course. 0.8 times z minus 1 times xz is simply 0.8, the coefficient again, times xn minus 1. So getting the difference equation, we need hz to be in the negative powers of z. Let's find the output yn given xn equals to unit step. So this is using z transform to find yz. By lookup table, the z transform of the unit step is this. If you really to have all the details, you need to say ROC of absolute of z is greater than 1. The reason being that this is a causal signal. Alright, but if we are sloppy, we will not write that, but you should write this all the time. Now, to find yn, basically xn is being sent to this system h of z. So y of z is equals to x of z times h of z. So we use this equation. We have h of z, we have x of z, and now we can multiply. This is x of z, this is h of z, and now let us see what is the output. Again, we have a trick. If this is in positive powers of z, and we want to do factorization, what we need to do is we have to bring one of the z here to the other side. Later on, you realize that this y of z over z, this z will be moved to the right hand side after the partial fraction expansion. Let's now perform the partial fraction expansion to get some expression that looks like a over z minus 1 plus b over z minus 0.9. You will see why these values of the pole later. This is basically performing partial fraction expansion, and what you see is that I first represent this as b of z and a of z as coefficients in positive power. So this 1 here is the 1 in front of z, 0.8 is to the power of z to the power of 0, this 1 is to the power of z squared, minus 1.9 and 0.9. Once we have in this form, then we can use MATLAB. RPK equals to the residual, and then we can put b and a. Now remember, I am using residual and not residual of z because now I'm expressing it in positive powers of z. Residual was used in the Laplace transform for partial fraction expansion. Now we are showing you that it can be used for z transform. Simply treat z as s in this example. So we use residual of b and a, the two arrays, to get RPK, and we get it in this form. 18 and minus 17 for r, p is 1 and 0.9. So what does p means? So this becomes p. So this p will be inserted here, and 18 is associated with the first coefficient, and minus 17 associated with the second. So 18 goes to where the first guy is, and now I use the color for green. The second guy goes to here. So minus 17 goes to here because it is associated with the second pole. This one. Now we have this almost in the correct partial fraction expansion, but remember that we have left this y over z in this form because we are now ready to move it to the right hand side, because the lookup table demands some form that looks like this, some a z over z minus p, where a is actually a constant that can bring out. Now finally, when we perform the inverse z transform, the 18 goes out, z over z minus 1 is simply un, minus 17 comes out here, z over z minus 0.9 is simply 0.9 to the power of n, and because the signal is causal, is un, because ROC is greater than 1 or 0.9 in this example. So this is the closed form solution of yn. I'll now do the second one, which is the cosine. Everything is the same. I have my hz, I have my cosine, and I use the z transform table to convert my cosine omega naught n to this expression here. So this is nothing but the lookup table for the z transform of cosine omega naught n. Again, I use yz over z. That's the trick. Put the z on the below first. This is h of z. And this is the cosine with part of this expression. Remember that this z here has been brought down to the left hand side. Again, we do partial fraction example, and I'm using MATLAB to solve it. You have to solve it by hand, of course, for the exams, but this is again I'm using residual and not residual z, because I am expressing this y of z over z as positive powers of z. I get my RPK. This is my R, this is my P, and K is 0. There's no value in K. Now, you have 6 values here. You'll notice that these values are complex conjugate of each other. They come in pair. The first one along with the first one here. So let's call this R1. Let's call the second one, sorry, this first one P1. And let's call the second one R2. And the second along here P2. Now, R1 must be associated with P1. R2 must be associated with P2. How do we use this? You look at the P's carefully. You have to find the P such that the imaginary part is positive, the positive frequency. Then you look at the corresponding R. Alright, and we can convert this value here from rectangle form into polar form. So 0.9877 plus J 0.1564, the absolute value is 1 and the angle is 0.05 pi. So you can now put it in this form. These 6 values are put into this representation because that's what residual is giving us. You will give the values of these coefficients in these forms. We have yz over z, but now we can throw away the denominator z as we bring it to the right hand side. Now this is ready to be performed by inverse z transform. The last one is trivial. The last one is simply R3, which is this value here, multiplied by P3, which is this value here, 0.9 to the power of n. What about these two guys here? The complex conjugate. You realize that in other lectures I've shown you that you can convert this pair into a cosine with a magnitude represented by R1 times 2, because there's 2 of them, and then it's an angle. This angle is this angle over from R1, because R1 can be extracted to perform magnitude and angle. So the angle theta came from R, and finally the omega naught came from this imaginary part of P1, which is 0.05 pi. I've also written my MATLAB code. Please take a look to see how you can generate the equations directly from the equations of B's and A's to generate the RPK, using the RPK to generate the closed form solution as well as the signal yn for n equals to 0 to n minus 1 using the cosine 0.05 pi given by omega naught here. Lastly, this is my MATLAB code to show you the surface of HZ. There is a pole at positive 0.9 and there is a 0 at minus 0.8. The vertical axis represents the magnitude of Hz in 20 log. So this is in log scale. And the red crosses here where I have shaded in yellow is the unit circle. So the surface of Hz is, you can visualize, and the important part is where the unit circle is. This shape would be the frequency response h of omega, or sometimes I write h of j omega. So this is the question for tutorial 5A, question 3. Thank you.